This is Donna Nelson at the University of Oklahoma, filming for my organic chemistry class. And this filmed lecture is going to be the final filmed lecture from Chapter 21 of David Klein's Organic Chemistry. And so in this final lecture from this chapter, we're going to be covering conjugate addition reactions and briefly synthesis strategies. So we've been building these reactions all along, learning all of these reactions, and now we're going to use a lot of them in this section 21.6 in combination. So we have in these the conjugate addition reactions, we have to recall that alpha-beta unsaturated carbonyls are made using the aldol condensation. So remember, this is where you go through the aldol intermediate and then you lose water across the alpha-beta position. This alpha-beta unsaturated carbonyls, these alpha-beta unsaturated carbonyls, each have 3 resonance contributors. So the beta carbon and the carbonyl carbon are both electrophilic. They both can be drawn in these resonance structures bearing a positive charge. So both of these positions are electrophilic. And so either carbon can be attacked by a nucleophile. It can be attacked selectively, depending upon the nucleophile used. So here are the 2 electrophilic positions highlighted in this structure to make it easy for you to observe what we're going to be doing. We're going to be attacking here. So many steps have gone into arriving at this alpha-beta unsaturated carbonyl, and now it can be elaborated further. So first, Grignard reagents or nucleophiles, such as Grignard reagents, where the alkyl group is attached to a highly electropositive metal, one of the metals lying far over to the left side of the periodic table. So this provides, you can think of it as an alkyl anion, although there's still quite a bit of covalent bond character between the carbon and the magnesium. But this you can think of it as providing an alkyl anion. And so this alkyl anion, which bears a large negative charge on carbon, will attack at the carbonyl carbon. And then you'll get the oxygen anion, the alkoxide, and then that will be protonated simply by dilute acid in order to arrive at the product that is shown here. This is called 1,2 addition. 1,2, 1,2 addition. Now we're also going to look at 1,4 addition. 1, 2, 3, 4. And so the 1 and 2 and 1 and 4 are simply relative to each other. It has nothing to do with the numbering of the atoms in nomenclature or anything else. So now we're going to look at 1,4 addition. And so remember, this carbon also can bear a partial positive charge. And the farther in this conjugated pi system, the farther away from the oxygen that one goes, the less the size of the positive charge. So this partial positive is a greater partial positive than that partial positive. And if you had another double bond, you would have another partial positive generated on out. So these, you would have to see this sort of charge alternation. And as you travel progressively farther away from oxygen, the partial positive charges would diminish, which makes sense because the oxygen is the one that's polarizing the pi bond like this. So here we have a partial positive charge on this carbon, which is less than the partial positive charge up here. So you have this carbon bearing a fairly large negative charge attacking at this carbon that bears a fairly large positive charge. Notice, as I said again, the magnesium lies far over to the left of the periodic table. Now you have an alkyl anion that is provided by this alkyl cuprate, also called a Gilman reagent, where the carbon is attached to copper, which is a transition metal. It's in the middle of the periodic table. And so this carbon does not bear such a large partial positive charge. The partial positive charge on this carbon attached to copper is a smaller partial positive charge. And so this carbon that bears a smaller partial positive charge will selectively attack here at this carbon, let me restate that. The carbon bonded to copper, which bears a smaller partial negative charge, will attack at this carbon, which bears a smaller partial positive charge. So the smaller partial negative attacks at the smaller partial positive position. Whereas up here, the larger partial negative carbon attacks at the larger partial positive position. I have to say that slowly in order to ensure that it comes out right. And so, of course, when the R minus attacks out here at the beta position, initially a negative charge will be formed at this alpha position, and you'll have an enolate. And then when reaction solution is neutralized, then that's protonated. So here are the mechanisms. Here is the mechanism of conjugate addition. You have the nucleophile attack the beta position. So this would be the 4 position in the 1, 2, 3, 4, 1, 4 addition. And so a negative charge is generated at the alpha carbon, and you have resonance structure stabilizing that anion. So the negative charge also resides on oxygen. Then oxygen is protonated to give you this enol, and then you have tautomerization to generate the keto form of the aldehyde. So there's the general mechanism. So if your nucleophile, if the carbon in your nucleophile is bearing a smaller partial negative charge, it will attack at the site of a smaller partial positive. If the nucleophile, if the carbon in the nucleophile is bearing a larger partial negative, then it will attack at the position at the carbon that is bearing the larger partial positive. So let's look at some other examples of that. Stronger nucleophiles tend toward 1,2 additions. That would be the carbonyl carbon. Less reactive ones, the ones that do not bear such a large partial negative charge, tend to react at the 4 position, because it has a smaller partial positive. However, you will frequently get a mixture. You won't always get just one product or the other. But so here we're talking about the major product, major and minor. So stabilized enolates, however, give 1,4 addition exclusively. And so here we've got the, here is the alpha beta unsaturated carbonyl. And so now we're going to generate the enolate here And this is going to be the carbon that's going to bear the negative charge. So here is the bond that's forming. And so you can see this carbon skeleton here in the product. And so the new bond that's formed is here. You can see the carbon skeletons of your two reactants easily. So this is what's called a stabilized enolate. And remember what I said about the carbons that bear a smaller partial negative charge will attack at the 4 position, and obviously this one is attacking at the 4 position, 1, 2, 3, 4, or at the beta position of the alpha-beta unsaturated carbonyl. And so this one also has a smaller partial negative charge at that alpha carbon, because when this is deprotonated, the negative charge that's generated will be spread out over all 5 of these atoms. You're going to have multiple resonance structures, and that will make the negative charge at this carbon atom lower. So once again, you'll have a reduced partial negative charge here. So it will attack purely at the beta position. So this conjugate 1,4 addition is called a Michael reaction. So this is called conjugate addition, when you have this addition at the beta position or addition at the 4 position, or you can call it 1,4 addition. So there are a lot of different ways to describe this, a lot of new terminology to learn just about this type of addition, but they all mean exactly the same thing. So you just have to become familiar with that different terminology. We've also got additional terminology now, a Michael donor, a nucleophile that does conjugate addition. That means adds at the beta position or adds at the 4 position, attacks at 4 position. You can also think of it as it donates a pair of electrons. That's why it's called a donor, a Michael donor. This will deprotonate. You'll have the negative charge spread out over all these atoms. The negative charge here will be a smaller partial negative charge, and so it will attack at the beta position, the 4 position. It will do conjugate addition. Then over here, this is called a Michael acceptor because it's accepting a pair of electrons. The pair of electrons comes in and it is attacked. This Michael acceptor, the alpha-beta unsaturated carbonyl, is accepting the pair of electrons. And so you can think of the terminology as sort of similar to the terminology in the Lewis acid and Lewis base discussions. So it's accepting a pair of electrons or donating a pair of electrons. So now we have a list of Michael addition donors and Michael addition acceptors. And so let's look at some commonalities in each of these lists. So first, let's look at the Michael acceptors. Over here you can see this is an alpha-beta unsaturated compound. And so this is alpha-beta unsaturated carbonyl in 4 of the positions. The others are not carbonyls, but they're very similar to the carbonyls in that here we have carbon that is doubly bonded or here triply bonded to a highly electronegative atom. And so this highly electronegative atom will polarize this entire pi system, generating a partial positive at that beta position. There's a partial positive on this carbon also. It's just not shown. Now in the nitro substitution, you're going to have an NO double bond and an NO single bond where nitrogen is bearing a positive charge and oxygen is bearing a negative charge. And so once again, the atom here that the double bond is attached to is bearing a positive charge, or as up here, a partial positive charge. And the oxygen that it's attached to is going to polarize this entire pi system. And so you're going to have the oxygen and the nitrogen with the positive charge, and then carbon with a partial positive charge. And so these all have that similarity in that the beta positions are all partially positively charged. These two are different because you don't have a carbonyl, but nevertheless, it's the same situation. And there are others. You'll just have to be able to recognize these patterns. So here you can learn the characteristics which are essential to be able to set up this pattern. Now, the Michael donors, look at what you have in the Michael donors. In most of these cases, you're going to have a pair of electrons in between two carbonyls. Here it's a pair of electrons, a negative charge in between a carbonyl and a nitrile, and here it's a pair of electrons that are on a carbon directly bonded to this nitrogen that is bearing a positive charge due to the nitro group. And so these each have the negative charge spread out. Here the negative charge is spread out by conjugation, and it's stabilized due to resonance. So once again, the negative charge is stabilized due to resonance in those 5 cases. And so in these 5 cases, this donor, the pair of electrons, is stabilized due to resonance. This, it is not resonance. Here the carbon is directly bonded to a transition metal that is not highly electropositive. And so the carbon-copper bond will be more covalent than, say, in a Grignard reagent. And so here the carbon is bearing a smaller partial negative charge because it's bonded to a transition metal atom. And it will be the same way for the other transition metals bonded to carbon. You'll have the same situation. So don't think of these as just the only examples. Think of these as a sufficient number of examples to give you a pattern to learn from so that you will recognize the characteristics. Don't just try to memorize these few examples. Now, on to the Stork-enamine synthesis. Because singly stabilized enolates, in other words, those with only one carbonyl, don't give high-yielding Michael additions. That's the attack at the 4 position, or the alpha-beta unsaturated carbonyl. The Gilbert-Stork developed a synthesis using an enamine intermediate. Here you have the enamine intermediate. And so this reminds you of how the enamine is created from the carbonyl. And we covered that back in chapter 19. And this can also be converted back to the carbonyl simply by using acid and dilute acid and heat. So this enables one to carry out the reaction and then regenerate the carbonyl, which is what you're going to see in just a second. So the conjugate addition reactions, here both of these will give conjugate addition reactions. So here this is an enolate anion and this is an enamine. So these are shown side by side here. to enable you to see the similarities. The important part for this purpose is that here at the alpha position, you have a pair of electrons and a negative charge. Here at the alpha position, you have a pair of electrons and a negative charge. So these two are similar, and you might expect them to be able to undergo similar reactions, and indeed they do. So an enamine is less nucleophilic, but it is still a Michael donor, and because this partial negative charge will be less than the partial negative charge on the other side. And remember, these are resonance structures, a pair of resonance structures, because only electrons move in resonance structures. So now, here we have your enamine shown as attacking at the beta position. So this is functioning as a Michael donor, a Michael acceptor, 1,4 addition, also called conjugate addition, so many different terms applied to this particular reaction. And so after conjugate addition, to give you the iminium group and the enolate, both of these can be converted back to the carbonyl, the carbonyls, rather, the two carbonyl functional groups using dilute acid. And so now the effect of this is as if the original carbonyl had done a 1,4 addition. So it's not really good at doing 1,4 addition, the original carbonyl. And so we sort of took this different pathway to achieve the same thing. So now we have the 3-step synthesis here. It has this additional step converting it to the enamine, in which gives the product as if this carbonyl had done the 1,4 addition itself. So we had to go through formation of the enamine, then the Michael addition, the 1,4 addition, and then hydrolysis. So these two steps had to be added, the formation of the enamine and then the hydrolysis to regenerate the carbonyl from the enamine. So now a different synthetically useful reaction is the Robinson annulation. And you know, annulation simply means to form a ring on something. And so this is the Robinson annulation. Occasionally it's called the Robinson ring annulation. And so this is a 2-step process. The Michael addition, which you're already familiar with, the negative charge is generated here, stabilized by the 2 adjacent carbonyls. So you have your negative charge stabilized. The negative charge here is a smaller negative charge, partial negative. And so it will attack at the beta position, doing a conjugate addition. And here is the new bond that is formed right in here. You can see the carbon skeletons of your 2 reactants there. And then you have a second deprotonation using sodium hydroxide. This is the proton that's removed over here. In this case, the proton that's removed over here is adjacent to this carbonyl. You're not going to remove any protons over here because this carbon already has 4 bonds to it. So this terminal carbon will be the one that is deprotonated, and then it is set up nicely for the carbon bearing this negative charge to simply attack at this carbonyl, forming an alpha-beta unsaturated carbonyl. So this is an aldol condensation where you will lose water across this carbon-carbon bond, forming the carbon-carbon double bond. And so These are steps that we've gone over individually. We've gone over the many steps that are included in this synthesis, but it may look a little more complicated here because we've combined so many of those steps into just this one little synthesis, which is very valuable. It's very valuable in synthesizing biologically important molecules. So now, synthesis strategies. Most of the reactions in this chapter are carbon-carbon bond forming reactions, and those are extremely important reactions in organic chemistry. Actually, in the long run, we don't have that many carbon-carbon bond forming reactions. So this chapter gives many valuable, synthetically valuable reactions. And they yield products that contain two functional groups. So the aldol reaction gives you a product that contains a ketone, rather a carbonyl, aldehyde or ketone, a carbonyl, and an alcohol functionality. The Claisen condensation gives a reaction that contains an ester and a carbonyl. Here, the Stork-enamine synthesis gives you a reaction that contains the amine and the carbonyl. And so this gives you this is a Michael reaction. The positions and identities of the functional groups in the target compound dictate which reactions and reactants can be used to synthesize it. And so we've learned two methods of alkylation now in this chapter, and the two can be combined. And so first, the alpha position of an enolate attacks an alkyl halide. That would put the methyl group on. The Michael donor can attack the beta position of a Michael acceptor. So notice, however, in these two, first we have the Michael donor attacking the beta position. So in this reaction, in this particular reaction, we covered them in this order, but in this particular reaction, the ethyl group is going to go on first. So you're going to have attack the beta position of the alpha-beta unsaturated carbonyl, and you will be left with an enolate. So a negative charge will be generated here. So you'll have the ethyl anion attack here, creating a negative charge here. That negative charge in the second step will then do an SN2 reaction on methyl iodide. So there's a lot of different combinations, a lot of different ways in which these reactions presented in this chapter can be combined to create very useful synthetic pathways. And so this is the conclusion of chapter 21, covering all of these synthetically useful reactions.